Good morning, professors, and welcome to a new experience with the ScienceBus ScienceBus. I am Barbara de Cicco, and in these videos, in collaboration with ScienceBus, I will illustrate the experience that can be conducted with the ScienceBus kit. Today, we'll observe and analyze the law of communicating vessels through an experiment. We'll need the thermodynamics and mechanics kits. This experiment is ideal for students in their first 2 years of high school. Let's move forward by positioning the system of communicating vessels securely in the plastic base. We then fill up the graduated beaker with precisely 100 milliliters of water. Next, we carefully add 2 to 3 drops of food coloring into the beaker. This step is simply to enhance the visibility of the liquid within the communicating vessels. Let's thoroughly mix it to ensure the liquid is homogeneous. We carefully pour the entire 100 milliliters of water into the system of communicating vessels and attentively observe that the liquid has uniformly reached an identical height in each of the 4 vessels, irrespective of their individual shape and cross-sectional area. The principle governing communicating vessels is fundamentally based on the essential law of fluid statics. Within a system comprising communicating containers filled with a liquid, the liquid level, when at equilibrium, will be at an identical height across all containers, irrespective of their individual shape or cross-sectional area. Within the system of communicating vessels, as you can clearly observe from the provided image, all the tubes are interconnected to a shared foundational base. When the system successfully achieves equilibrium, the pressure at the base, specifically the pressure at the lowest point where all the tubes converge, is uniformly identical for each of the tubes. The hydrostatic pressure fundamentally depends exclusively on the depth h, which is the vertical height of the water column situated directly above that specific point. As we have previously mentioned, the pressure at the lowest point of the conduits, and consequently the pressure at points 1, 2, 3, and 4, remains consistently the same. The governing law applicable to liquids, which establishes the relationship between pressure and the height of the liquid column, is known as Stevens' law. In accordance with Stevens' law, the hydrostatic pressure is determined by the multiplication of the density R, the gravitational acceleration G, and the height h, with the subsequent addition of atmospheric pressure to this calculated product. In our scientific experiment, we are capable of equating the pressures at points 1, 2, 3, and 4 by observing that the atmospheric pressure within each conduit of the system remains consistently aligned with the density of the liquid and the gravitational acceleration. We derive the equality relationship among the 4 distinct heights. This comprehensive explanation clarifies what we have understood through our experimental procedure by introducing the liquid into the communicating vessels. It reaches an equivalent height in each conduit, regardless of their shape and size, precisely because the pressure at the base remains consistently uniform. At this juncture, we possess the capability to ascertain the hydrostatic pressure by gauging the height attained by the liquid. Utilizing a marker, we indicate on the communicating vessels the level achieved by the 100 milliliters of water. Now, let us proceed to replicate the experiment by meticulously pouring 100 milliliters of an alternative liquid, such as vegetable oil or perhaps alcohol, into the beaker. Subsequently, we will denote the height attained by these distinct liquids. We will observe that as the density of the liquid increases, the height achieved by the liquid will proportionally decrease. Conversely, a liquid with lower density will reach a significantly greater height within the communicating vessels. Professors, thank you. We'll see each other at the next experiment. Goodbye.